Imagine a world so far away that light from our sun takes over 5 hours to reach its surface. Out here, a single year drags on for 248 Earth years. The temperature routinely drops to -230 degrees Celsius, a cold so absolute that liquid water would instantly freeze into a material harder than solid rock. For a long time, this was a completely hidden world. That changed in 1930, when a 23-year-old American astronomer named Clyde Tombaugh spent months meticulously comparing photographs of the night sky, looking for a tiny speck of light that moved against the backdrop of distant stars. An 11-year-old girl in England named Vanessa Burney suggested calling this newly found speck Pluto, after the Roman god of the dark underworld. The name fit the freezing, remote environment perfectly, and it kicked off a 76-year reign as our solar system's 9th planet. For decades, humanity operated on a very basic assumption. Because it was small and far away, we assumed Pluto was a static, dark ice ball sitting at the very edge of our solar system. That perception shifted in 2006. Thousands of scientists gathered in Prague for an International Astronomical Union meeting, ready to cast a vote that would officially redefine the architecture of our solar system. The Union established clear criteria for planetary status. First, a body must orbit the Sun. Second, it must have enough internal gravity to pull its mass into a round shape. Pluto meets these first two requirements. Then comes the third rule. A planet must prove its gravitational dominance by clearing its orbital neighborhood of other large objects. Pluto fails this test. It sits deep within the Kuiper Belt, sharing its path with thousands of other large, icy bodies. Failing that final requirement triggered an immediate reclassification. Pluto was stripped of its status and officially named a dwarf planet. Just as the scientific establishment wrote Pluto off as a lesser world, NASA launched a deep space mission that would soon prove our previous understanding of the surface was largely incomplete. This was the launch of the New Horizons spacecraft. Fired into the vacuum at roughly 58,000 kilometers per hour, one of the highest speeds ever achieved by a human-made object, it still took 9.5 years to reach its target. As the probe approached, scientists prepared to document what they expected to find. Because Pluto is smaller than Earth's own moon, the prevailing theory held that it would be a gray, heavily cratered rock. The 2015 flyby provided a very different reality. Pluto is covered in striking shades of red and brown. The color comes from a complex chemical reaction. When ultraviolet light from the sun hits the methane in Pluto's atmosphere, it triggers the creation of falling organic compounds called tholins. These particles slowly rain down, coating the ice in a reddish-brown dust. Finding active organic chemistry on the surface immediately replaced the image of a cold, gray rock with something much more complex. That discovery challenged another long-standing belief, the assumption that a world this cold must be geologically dead and frozen solid. Then, New Horizons transmitted images of Tombaugh Regio. This massive, bright area is shaped like a heart. It is roughly the size of Texas and is composed entirely of nitrogen ice. The material composition here behaves differently than on Earth. Surrounding the heart are jagged mountains towering 3 kilometers into the sky. On Earth, mountains are rock. On Pluto, they are made of water ice, frozen so thoroughly that it acts structurally identical to stone. Contrast those rigid water peaks with the valleys beneath them, active, flowing glaciers. Because nitrogen freezes at a much lower temperature than water, these massive sheets of nitrogen ice are slowly creeping and weaving between the stationary mountains. Pluto is geologically active. Its landscape is slowly reshaping itself in the deep freeze of space. We also assumed that a dwarf planet isolated in the Kuiper Belt would be a simple, lonely rock, lacking the atmosphere or complex moon systems seen in larger worlds. Even its path through space is unusual. As this orbital diagram shows, Pluto's trajectory is highly elliptical. For 20 years out of its 248-year cycle, it actually crosses inside Neptune's orbit, bringing it closer to the Sun. This creates a unique breathing atmosphere. When Pluto moves closer to the Sun, The slight increase in heat causes surface ice to sublimate into a nitrogen gas atmosphere. As its orbit pulls it back out into deep space, that gas freezes and falls back to the surface as snow. It also hosts an intricate system of 5 moons. The largest, Charon, is so massive relative to Pluto that the two bodies actually orbit a shared center of gravity in the space between them. By hosting a multi-moon system and a cycling atmosphere, Pluto exhibits a level of complexity that rivals many of the official planets. The New Horizons data points to a theory involving what we can't see. Deep beneath that thick crust of frozen water and nitrogen, Pluto might harbor a vast liquid subsurface ocean. Looking at this cross-section of the planet's internal structure reveals the physics behind it. Pluto's rocky core contains radioactive elements. As these elements decay over billions of years, the process generates a slow, steady heat. This thermal energy radiates outward, melting the bottom layer of the ice crust and trapping a layer of liquid water underneath. We see similar environments on our own planet. Deep-sea volcanic vents on Earth provide the chemical energy necessary for microbial ecosystems to thrive in total darkness, entirely independent of sunlight. This internal heat and the potential for liquid water suggests that Pluto possesses the primary components for a habitable environment: liquid water and a consistent energy source at the very edge of our solar system. Because the spacecraft moved too fast to enter orbit, we only captured a brief glimpse before it vanished deeper into the Kuiper Belt. Returning for a more detailed study remains technologically difficult for perhaps the next 50 to 100 years. We are left to reconcile these high-resolution images with our human-made labels. Pluto's geological and atmospheric diversity proves that our rigid scientific categories often struggle to capture the reality of the universe. A celestial body does not need an official title to be one of the most uniquely complex places we have ever observed. Pluto continues its long, slow orbit in the dark, a distant world with its own internal heat and a surface that is still changing, reminding us how much of the cosmos is simply waiting for us to look closer.